Welcome back, everyone. Today's lecture, I think, is going to be one of the most mathematically challenging lectures of the semester. I'm going to talk about a sort of amazing trick called the kernel trick that's used in various parts of machine learning for both regression and classification. And to motivate this, I want to recall what happens when we use polynomial, like higher degree features. So let's suppose that you have input points in d-dimensional feature space, and you don't want to just do linear regression or linear decision boundaries on them. You want to use degree p polynomials. Well, what that does, of course, is it increases the number of features a lot. If you want fully general p-degree polynomials, then what you do is you replace your d-component feature vectors with lifted, and the lifted vectors each have something on the order of d to the power of p features. So, you know, if you want to do fourth order polynomials, degree 4 polynomials, then you are blowing up the number of features to d to the power of 4. So that seems pretty limiting if the number of features itself is large. Like, let's suppose that you have 100 features for each input vector, for each sample point. Then using degree 4 decision functions means now you have to lift up each point to a point with a length of 4 million components for each sample point. So this gets computationally intractable pretty fast as the polynomial degree rises, unless you use kernels. So what we're going to do today is something that still seems magic to me. We are going to use those 100 million features without paying for them, without computing them. We're going to look at a cheap alternative that doesn't blow up with the degree of the polynomial. And this is based on 2 observations that apply to many, but certainly not all, learning algorithms. So the key observation, which I found a bit surprising when I first heard it, is that there are a lot of learning algorithms in which once you compute the weights, they can be written as a linear combination of the sample points. And the second property of a learning algorithm that you need if you want to apply the kernel trick is that there has to be a way to implement the algorithm so that you don't ever actually need to compute the lifted vectors explicitly, because all the computations that you do only need inner products of these lifted vectors. So again, the key is that I don't need to compute the lifted vector phi of x. Because I don't want to compute a feature vector that's 100 million components long. But we will have a way to compute these inner products of those very long feature vectors in a very short amount of time. So coming back to the first one, when I say that the weights can be written as a linear combination of the sample points, we can actually write that down as a formula. Let us suppose that W is equal to, and by W I mean the optimal weights that your learning algorithm will learn. Suppose that that's equal to X transpose A for some vector A. And let me write that out as a summation, just so that we can see totally clearly that what this is a linear combination of the sample points. And so the AIs, the components of this vector A, are just the coefficients of a linear combination of sample points. And what I'm claiming is that the optimal W, if you have an algorithm where the optimal W always takes that form, you might be able to use this trick. So this has to be true for some vector A in n-dimensional space. So if we know that we have an algorithm that has this property, and I will show you soon that several of the algorithms we've already learned do have this property, then what we can do is we can substitute this identity into the algorithm or into the objective function of the algorithm. And now we have an optimization problem in terms of A rather than an optimization problem in terms of W. And so we solve that optimization problem in terms of A, which means that now we are optimizing n dual weights, is what they're called. The elements of A, the components of A, are called dual weights. Or sometimes you'll see them called dual parameters. Instead of optimizing for our original D weights, or actually D plus 1 weights if you're using, a fictitious dimension, as you probably should be, or D to the power of P weights if you're using polynomial regression. And so the usual weights that we've been using all semester, the weight vector W, we're going to call those the primal weights to contrast them with the dual weights A. But when you apply the kernel trick, we're no longer optimizing in terms of the primal weights. We now want to optimize in terms of the dual weights instead. And once you find an optimal value of A, well, you can go back from the dual weights to the primal weights just by plugging it into this equation, and that gives you the primal weights W. So to make this concrete, let's kernelize an algorithm. And the first algorithm that I want to work on is ridge regression. So we're going to develop now an algorithm called kernel ridge regression, which is intended to give you the same result as primal ridge regression would give you, only in some cases much faster. All right, so for ridge regression specifically, there's one problem that I have to deal with, which is that remember I said that for us to apply the kernel trick, you have to have this property, that the weights can be written as a linear combo of the sample points. Well, there's a technicality in ridge regression. This is true if my L2 regularization term penalizes the bias term as well as the other weights. So I had said earlier that you don't really want to penalize the bias term. Well, here we're going to have to make an exception. We're going to need to penalize it to get this property to be true. So in order to make up for the fact that we're going to be penalizing the bias, I want to penalize it as little as possible. And so one way to reduce any bad effects that might happen from that is that I center x and y first before we run the algorithm. So let's just add a little centering step at the beginning to try to reduce the bias caused by penalizing the bias term. And so essentially that means that each sample point, xi, is replaced by xi minus the mean sample point. Each label, yi, is replaced by yi minus the mean label. Remember, we're doing regression, so those labels are continuous valued. And also, we do want to have a bias term. We do want to have a fictitious dimension. So that means that at the end of the matrix X, we're still going to have a column of ones, like usual. And you just need to remember not to center that column of ones, because if you apply centering to the column of ones, you get a column of zeros, and your method will not work. So when I say center X, that column of ones at the end has to remain a column of ones and not get centered. All right, so the reason why we're centering is because it minimizes any bad impact that might happen when we replace I prime with I in the normal equations. And let me remind you what the normal equations are for ridge regression. They are, you'll recall, x transpose x plus lambda I times w equals x transpose y. So that's the ridge regression equation. You solve that equation for w. But I told you before that we should use not the identity matrix, but a modified identity matrix where we put a 0 at the very bottom right so that we don't penalize the bias term. Well, now, unfortunately, we have to penalize the bias term, so that's what we're going to do. We just have I here instead of I prime, the standard identity matrix. All right, so let's look at how we could solve that with dual weights. Well, suppose that our vector of dual weights A is a solution to the following equation. You notice it's very similar, but x to x transpose, the right-hand side also changed. But it's a very similar equation. So now what I want to do is I want to convince you that this solution A is going to give us a solution to the original normal equations that we're trying to solve as well. So by solving the dual problem, we get a solution to the primal problem. And to show that, what I'm going to do is I'm just going to take this value of y, and I'm going to essentially substitute it there, multiply it by x transpose in front. And when I do that, I get x transpose y. Well, substitute this in for y, and you get x transpose x transpose a, plus lambda x transpose a. And we can pull that apart into this form here. And so you can see that this equation here, that equal to that, is a match for the primal ridge regression equation, normal equations that we want to solve, as long as we just set w equal to x transpose a. Therefore, if we set w equal to x transpose a, then that is a solution to the original normal equations for ridge regression, albeit with the bias term penalized. Moreover, this solution that we have found to the primal equations also satisfies what I told you is a precondition for the kernel trick. So we have verified that this particular algorithm, ridge regression, where you penalize the bias term, does indeed have this property that the weights can be a linear combo of sample points. So let me just say that again, because that conclusion is really important. W is, we have shown, if you solve it this way, you always get a linear combo of the sample points. All right, so again, we refer to A as, well, remember these are the dual weights, so this particular A is a dual solution. It solves not only the normal equations of the primal form of ridge regression, it also can be cast as an optimization problem on its own. Here is the dual form of ridge regression. We can write it as an optimization problem as well. The value of A that is the solution to this linear system is also a value of A that minimizes this objective function. And you might ask, where did this objective function come from? Well, just remember that the primal ridge regression objective function is just xw minus y squared plus lambda w squared. That's our standard ridge regression cost function. And so if you just simply substitute w equals to x transpose a into there and there, well, you get this. So that's the mathematical connection between the primal problem and the dual problem. How does this lead us to an algorithm? Well, it's very simple. Our algorithm is going to be as follows. The training part of the algorithm is just solving that linear system of linear equations I gave you. So here we know x, we know y. The only thing we don't know that we need to solve for is a. So we solve this linear system of equations for a, and then to use our classifier that we've just trained. All right. What is the regression function that we have just learned when we trained this classifier? Well, remember that we're doing linear regression, so the hypothesis at any test point z is going to be the primal weights dot product with z. Now, we didn't solve for w, we solved for a, but that's okay because we can get w just by substituting x transpose a. If we do that here, that comes out as a transpose times x times z. So that's what we need to compute to get a solution out of these dual weights A. Now, I want to take this one step further because remember I told you that there is a second requirement for using the kernel trick. And the second requirement is we can use inner products of the lifted feature vectors without actually computing the lifted feature vectors. So right here, if I want to use lifted feature vectors, then that matrix there is going to be really, really big. It's going to have rows that are 100 million components long. We don't want to work with that directly at all. We never want to write out that lifted version of X directly. But there's a trick here. We can express this little product of vectors and matrices as the following summation. So this summation has one term for each training point, xi. And important thing to notice is that this is an inner product. And I'm going to try to convince you later that we can compute that inner product without actually computing xi in certain circumstances. And that's where the magic will happen. But anyway, for now, what you want to know is you can interpret this as a weighted sum of inner products. All right, so now what I want to do is I want to write out this algorithm in more detail with focus on the inner products that I'm going to use, because those inner products are what's going to make the algorithm fast. So let's think about this a little deeper. First of all, I'm going to define something called the kernel function, which we're going to denote with a lowercase k. So the kernel function takes in two vectors, x and z, having the same length, and it does something with them. Right now what it does is just an inner product. But later we're going to change that. Later what we're going to do, to be precise, is we're going to replace x with phi of x, and we're going to replace z with phi of z. And those phi's will be very, very, very long vectors, maybe even infinitely long. And that's where the magic will happen. But for now, pretend they're just normal vectors, normal feature vectors, that we want to find their inner product. Once you've defined a kernel function, then we're going to define a kernel matrix that involves all pairs of sample points run through or all pairs of training points run through the kernel function. So one way to write it is, given a design matrix X, the kernel function is X times X transpose. And this is an n by n matrix, again, called the kernel matrix. And the reason we're calling it the kernel matrix is if you look at any particular component, row I, column j of the kernel matrix, then that is the kernel function applied to training point xi and training point xj. One thing I want to note is that k obviously is always going to be positive semi-definite, but sometimes it's going to be singular. Sometimes it will have eigenvalues of 0. One particular case where that happens is if the number of sample points is greater than the number of dimensions. which often happens in normal problems, but if you blow up the number of dimensions to exponential, then it doesn't happen. But quite often k is singular, and remember, we want to solve this equation. This XX transpose is the kernel matrix K. If lambda is 0, then if K is singular, then that linear system might not have a solution. And so if you have a singular K, which comes up very often, then you need to use at least a small, you need to use some lambda that's greater than 0 to solve this linear system. So in this case, there's probably no solution to the linear system. If you set lambda to 0, so you have to choose a positive lambda, but that's okay. All right, the reason why I wrote out this kernel function and this kernel matrix is so that I can rewrite my dual algorithm so that it does not depend on the lifted feature vectors directly, so that I can just write it in terms of the kernel function. So here's how to write the dual ridge regression algorithm using the kernel function. The first step is we explicitly build the kernel matrix. By computing each entry with this kernel function. Then we solve our linear system again. But remember XX transpose, now we can just write that as K, the kernel matrix. So we solve that for A. And that essentially is the training phase of the algorithm. Once you've trained your regression, then you want to use it to label points, test points. So the testing phase someone gives you a test point Z and says, regress this for me. What's the hypothesis at this point? And so you compute that linear combination of inner products, that weighted sum of inner products that I already told you about. And that's the testing phase, or the let's use what we've trained phase of the algorithm. I want to make some comments about the running times of these different steps of the algorithm. So computing the kernel matrix, that's big O of n squared d time. Because there are n squared entries you have to compute, nothing you can do about that. Each one is an inner product taking d time. The solution of a linear system, practically speaking, that generally takes n cubed time. And then for each test point, it's going to take order nd time to give the label for that test point. And I don't know how many test points you have, so I left that out, but nd times the number of test points is going to be the running time of the test phase. Now again, I want to emphasize what we accomplished by plugging in this kernel function in this kernel matrix is now I've just written pseudocode that does not use the sample points directly. It only uses them in the form of inner products and the kernel function. So that's going to become important soon. I want to re-emphasize the fact that this dual ridge regression algorithm produces the same answer as the primal ridge regression algorithm if you penalize the bias term in the primal ridge regression algorithm. So we're not doing this to get a new algorithm. We're using this to get ridge regression, but make it faster in certain circumstances. And so you might ask, what circumstances is it faster? What circumstances is it slower? Well, let's compare the running time of the dual and primal versions of ridge regression. Well, in the dual algorithm, you need to solve an n by n linear system. And the total running time is going to be big O of n cubed plus n squared d. Where did I get that from? I'm just adding these two together. Let's compare that with the running time of the primal ridge regression algorithm. There, we're solving a d by d linear system. You'll recall that the matrix we get out of that is d by d. So essentially, n and d trade places in this complexity. So looking at those two big O's, that gives you a pretty solid idea of when you would prefer the primal algorithm and when you would prefer the dual algorithm. We prefer the dual algorithm when d is greater than n. In other words, the number of features you have is greater than the number of training points. Now, you might be thinking to yourself, in the vast majority of machine learning problems, we have way more training points than features. And that's true, which is why we very often still want to use the primal algorithm. But when we use polynomial features, remember the number of features blows up to maybe 100 million, and then suddenly this becomes true. So then we want to use the dual algorithm. But there's an additional catch that we're going to see next, which is when we use polynomial features and we go from, say, 100-dimensional feature space to 100 million dimensional feature space, we will find that with the dual algorithm, this d stays 100. It doesn't blow up to 100 million, whereas these d's here, they blow up to 100 million. So in that case, the advantage of the dual algorithm over the primal algorithm is going to be even bigger, almost unfathomably bigger. All right, sorry I still haven't actually gotten to the kernel trick yet. It takes a long time to set the stage. But are there any questions so far? Mm-hmm. Why do we center the data matrix again? So I have this general feeling that in most real-world problems, you don't want to penalize the bias term. But to do the dual algorithm, you have to penalize the bias term. So what I would like to do is minimize the harm done by penalizing the bias term. When you center both x and y, so you center your data matrix and you center your labels, then if they say, for instance, those come from a random distribution, like a normal distribution, then the expected value of the bias term is 0. Or the expected value of the optimal bias term that would be computed by ridge regression is 0. That doesn't mean that the actual answer is supposed to be 0. It just means that over many different data sets, you would get a 0 on average. So that is our intuition for why centering the data means that the bias term is likely, like the optimal bias term, is likely to be closer to 0. And if the optimal bias term is likely to be close to 0, then penalizing the bias term doesn't change the answer as much as it would have if the optimal bias term was huge. Yeah? Say that one more time. Oh, so you're asking about what if I modify this so that I'm not making the bottom right element 0, but I'm making it smaller than 1? In that case, I still do not know how to achieve the result that the weights can be written as a linear combination of sample points. If I knew how to do that, then I would do it, but I don't. So I think I'm stuck with the identity matrix. Someone writes a new paper that tells me how to do it. Yeah. The reason we want to penalize the bias term now is because it's the only way that I know to achieve this property, and without that property, we can't do the magic trick that we're about to do. That's really all there is to it. Yeah? Does it matter how much we penalize it? Well, I think the more you penalize it, the more suspicious your answer is. But that is an application-dependent thing itself. So it's hard for me to say something truly general. There might be some applications where penalizing the bias term is actually good. I can't be too categorical about that being a bad thing. For the kernel trick to work, you need to use the identity matrix in that linear system of equations, and I don't know any way to change that. Yeah, that's the bottom line. Mm-hmm. Uh-huh. Yeah, alpha. Generally, yeah. Right now we're doing regression, so it's slightly different. The reason we need a bias term is so that we don't force the regression function to be 0 at the origin. But that's almost the same thing. But go on. Mm-hmm. I don't know if you're conflating two different things. There's the question of whether we use a bias term or not at all. And there's also the question, do we penalize that bias term? Are you just asking about the second one?
Yeah, yeah. I guess I'm conflating the two because I know there's like scenarios in which we use a bias term and
Mm-hmm.
we're not supposed to use a bias term.
Yeah.
And here it seems like we're not we're assuming that we don't need it very much.
Oh, that's not right. But with the framework I'm talking about now, you can have a bias term if you want it. You can leave out the bias term if you want to. If you leave out the bias term, then just like with regular regression, you're going to force the regression function to be 0 at the origin. So that's your choice. You can have a bias term. You cannot have a bias term. But if you want to have a bias term, we have to penalize it to do dual ridge regression. And that's going to distort our answer a little bit. We maybe won't have quite as good an answer as we would have had. But hopefully it's not a big change. All right, so now I want to get to the magic part. Sometimes this is called the kernel trick. Sometimes this is called kernelization. You see various words out there. The trick itself, well, one version of the trick is that we can compute a polynomial kernel that involves many, many monomial terms without ever computing those many, many monomial terms. So we can lift a point to 100 million dimensional space and only pay for 100 dimensional space in terms of computing time. Here's the magic that does that. We're going to replace our kernel function with a different kernel function, polynomial kernel. Suppose you want degree p polynomials. Well, then you use the following kernel. The kernel function given two vectors, x and z, both of length d, is x transpose z plus 1. Note that that's going to be a scalar. X transpose z is just an inner product. It gives you a scalar. And then we take that scalar to the power of p. So we're going to substitute this kernel function into the dual ridge regression algorithm I just taught you. Why? What does this accomplish? Well, here is the key observation that makes it all work. This expression, x transpose z plus 1 to the power of p, is equal to a lifted vector x, inner product with a lifted vector z, where the lifting that we're doing, the lifting map, contains every monomial in x of all degrees from 0 up to p. So to put it another way, computing this thing is equivalent to computing an inner product of the featurized vectors we use for polynomials. I'm not going to prove this in the general case, but I think that if you just see it for a very simple case, it will probably convince you that this is true in the general case. Let's consider an example where you have just two features per sample point. So we've got a two-dimensional feature space, d equals 2. And let's suppose we're using quadratic polynomials. We want to do quadratic interpolation. So p equals 2. That's our polynomial degree. In that case, observe that if I write x transpose z plus 1 squared, and I expand out that square, I will get 6 terms. There's x1 squared z1 squared plus x2 squared z2 squared plus 2 times x1 z1 x2 z2 plus 2 times x1 z1 plus 2 times x2 z2 plus 1. So those are the 6 terms you get when you expand out both the inner product and the square. So now what I'm going to do is I'm going to turn that long thing into an inner product, where I'm going to take an inner product of a vector that depends only on x with an inner product of a vector that depends only on z. And so that'll be here's a vector where the first component is x1 squared, the second component is x2 squared. Let me give a little more space there. And here are the rest of the components. And I'm going to take the inner product of that with another vector that has the same components, only x is replaced with z. All right, I hope you can see how that line follows from the previous line. And so I will now just write that as an inner product of phi of x times phi of z. And I never actually formally defined what phi is now, but I'm defining it now. I define phi of x transpose to be this, and I define phi of z to be that. And so what you'll notice is that I have shown that this thing here is equivalent to writing out all of the different monomials in x1 and x2 up to degree 2, degree 0 to degree 2. Inner product with the same thing. But you might say notice that there's one thing here that is different than the way I taught you to do polynomial features back in lecture 4, which is now I've got these weird constants popping up, these square root of 2's. So when you do the kernel trick for polynomials, you don't really have control over those constants. You're going to get funny, especially when you go to higher degrees, you're going to get a bunch of funny constants stuck in there. But they don't really matter because the algorithm can compensate for those just by scaling the primal weights. Even though we're not explicitly computing the primal weights, we're just implicitly computing them, the algorithm can nevertheless adjust itself to make up for those. So the fact that we have some constants in there doesn't really matter. This is still going to allow us to do polynomial interpolation of general degree polynomials. So what did we just accomplish? Why is this a good thing? There is a big, big win here, which is that I can compute the kernel, the inner product of phi of x and phi of z, in big O of little d time instead of big O of d to the power of p time. Even though those phi of x and phi of z have a length that's d to the power of p. So I'm saying this is a really long vector. a really long vector, I can compute this really fast without computing those really long vectors. In fact, I can compute that so fast it's sublinear, exponentially faster than I can simply write out those long vectors. All right, so if you want to do kernel ridge regression with polynomial features, essentially all we do is we replace the original feature vectors xi in our algorithm with the lifted feature vectors phi of xi. So now instead of the kernel function being x transpose z, now it's phi of x transpose phi of z. Yeah.
Why is the complexity reduced when we know bigger of these, it's like 5x? We still need to compute each of those individual terms.
So are you asking why does it take big time to compute this? Yeah, okay. Well, x is a vector with length d. Z is a vector with length d. Computing the inner product takes time d. Adding 1 takes time constant. And remember, this is a scalar. Squaring a scalar takes time constant. That's all you have to do. So the point is we never have to deal with these long vectors at all. We go around them. So again, the big point I'm trying to make is that we don't compute those phis ever. That would be too expensive. They're 100 million elements long. Instead, you just compute this thing, and this only takes little o of d time. So I think what we've done here is actually pretty mind-blowing. We can now do polynomial regression with an exponentially long high-order polynomial in much less time than it would take just to write out the final polynomial that we have found. The running time is actually sublinear in the size of the polynomial that we find. Any more questions about that? Yeah. Uh-huh. Well, I mean, yeah, so the kernel function always does compute a scalar. I don't know what you mean by constant. I mean oh, okay, okay. Yeah, this is, the kernel function always computes a scalar. That's right. So, I mean, if you go back to the algorithm that we are using this in, this line here, yeah, that's just computing one scalar. We have to repeat that n squared times to compute the whole kernel matrix with every pair of sample points put together. Does that answer your question? Okay. Yeah. Yeah, that's right. If we didn't have this trick, then this would be replaced by d to the power of p. And so, yeah, that step would be very slow. Would be really slow, too. That would also be d to the power of p. Let's kernelize another algorithm. We've seen one kernel algorithm, and that is ridge regression. Let's do kernel. The original used. Or in other words, lifted sample points. So remember, the starting point is just an arbitrary number that's not 0, but as I pointed out before, I think it's useful to choose this starting point because it means that at least when you start, you have one correctly classified point with your initial weight vector. Then the perceptron algorithm looks for some misclassified point, and when it finds one, it updates the weight vector by adding step size times yi xi. Well, now this is going to be phi of xi because we're lifting it into higher dimensions. And then that's the training phase. Here's how you use the perceptron classifier after you have trained it for each test point z. The hypothesis at point z is just the weights times phi of z. Again, the first 3 lines are how we train the perceptron. The last 2 are how we use it after it has been trained. All right, to featureize this, we need to do some mathematical transformations on this thing. The first thing is we have a design matrix X. It's now going to be useful to have a like matrix, a design matrix for the points after we lift them into high dimensional space. So I'm going to call that phi of x. Applying phi to the whole design matrix X is just like applying phi to every row of the design matrix. In other words, applying phi to every sample point. So when we do that, now we're going to get an n by capital D matrix. Capital D is going to be the size of the lifted, featureized points. And so the rows of that matrix, phi of x, are going to be phi of xi with a transpose, so because those are column vectors. Again, D is just the number of components of each point after we apply the lifting, after we add the extra features. And since we're using the lifted points, since we're running our learning algorithm on the lifted points, now the kernel matrix is going to be based on the lifted design matrix. So nothing really special here. It's just that we're applying our algorithm to the lifted points instead of the original input points. All right, so when we dualize, we're going to have a weight vector that is a linear combination of the lifted points. So this just says that the weight vector is going to be a linear combination of the lifted sample points. Now, with this dualization, suppose I write the following line of code, which we will need for our algorithm. If you write a line of code that updates one dual weight, A of I, by adding the learning rate times Y of I, that has the same effect implicitly as this line of code right here in the primal perceptron algorithm. So we're going to be able to replace this line of code in the primal algorithm with this line in the dual algorithm. And this is implicitly true because this is how we define W. The last thing that we're going to need for this algorithm is I need to replace this with something that does not involve W, but involves A. This inner product between phi xi and W, well, I note that we can write this as taking the whole lifted design matrix, phi of x, multiplying that whole matrix by the vector W, and then just pulling out the ith component of the vector that we get in that matrix vector multiplication. And now if I substitute in my value for W, meaning substitute this for W, then we get phi of x times phi of x transpose times A, pick out the ith component, and we recognize that product of those two matrices as just being the kernel matrix. So this boils down to just take the kernel matrix, multiply it by the dual weights, pull out the ith component. Yeah, question? The transpose is supposed to be outside the parentheses for the phi. So we're computing the lifted design matrix and then taking the transpose of that. Oh, yeah. You're right, thank you. So, sorry, no transpose there. The transpose goes there. Yeah. All right, so putting this together gives us the dual perceptron algorithm, which is going to work like this. First step, I need to initialize the dual weights. Probably anything that's not 0 will do, but here's what I suggest. Take a vector that's all 0 except that the very first element is y1. And so this line of code has the same effect as this code in the primal algorithm. Next, we need to adapt. Well, before we adapt the rest of the primal algorithm, we need to compute the kernel matrix. So for every index I and j, the component in row I and column j of the kernel matrix is the kernel function applied to xi and xj. All right, next we're going to take these two training lines and convert those to the dual algorithm. And so in dual, those are going to look like this. While there is some index I such that this is negative, meaning that lifted sample points phi of xi is misclassified, then we update the index dual weight number I. All right, that's the training part. Now I want to take these two lines of test code from the original perceptron algorithm and dualize those. That is going to be for each test point z. So this line is actually exactly the same as it was for ridge regression. So this part hasn't changed at all from ridge regression. Except, well, what you really want is the sign of this. You want to return the sign. That tells you what class you pick. But this is the actual value. So there's our dual perceptron algorithm. Now I want to look at the running time of these lines of code again. So this line of code takes big O of n squared times d time. And I want to emphasize that's little d, it's not big D. And the reason it's little d is because of the kernel trick. Now, this line of code here, it only updates one index. It literally takes constant time. So in a sense, it's very fast. But it's part of a loop. And the loop tests this condition. And this condition requires you to compute Ka. And I need to point out that you are literally changing A on every iteration of the loop. So that seems to imply that we need to recompute Ka every iteration. But we don't actually need to recompute Ka from scratch, which would be slow. We are only updating one entry of A, and therefore it is possible to update Ka to reflect that changed entry in order n time rather than order n squared time. The details of how to do that I'll leave as an exercise, but I just want to point out that there is a trick that keeps this from being unnecessarily slow. Every time you update an index AI, you can update Ka to its new value in order n time. So that's training. For testing, this line of code is going to take order nd time, again because of the kernel trick. Or I should say, that's a little d, not a big D, because of the kernel trick. And so again, it is a big deal that these depend on the length little d of the input sample points and not on the length big D of the lifted sample points. Yeah? Right. Instead of the what? Uh-huh. I don't think that the lines right before this are what's relevant. I mean, the relevance of these lines is that the fact that this is equal to this is what gives us this, and the fact that this has the effect of this is what gives us that line there. So that's what I get from writing these. The kernel matrix itself is, defined the same way, is defined this way. So you need a kernel function that computes the product of that computes this product in O of little d time, But we have that. That's the reason why we can compute that fast. Okay. One thing you might remember is that logistic regression is actually very similar to the perceptron algorithm. In particular, the way we got from the perceptron algorithm to logistic regression is taking this line of code and modifying it a little bit by adding a logistic function. Now, there are some other differences, like, for instance, the perceptron algorithm only looks at misclassified points. The logistic regression algorithm looks at all the points when you do stochastic gradient descent. So just remember that what logistic regression is going to do is it's going to process all of the points in a stochastic sort of random order. But with that in mind, here is the gradient descent step that we do for stochastic gradient descent on the logistic regression cost function. Where here S is the logistic function. And so again, if you compare this line of code in the perceptron algorithm with this line of code in stochastic gradient descent, the difference is just we've thrown in this logistic function here. And likewise, we can also derive a batch gradient descent version of logistic regression. Which looks even simpler. Now, here I should mention that our logistic function is now applied component-wise to a whole vector. And lastly, there's a minor change to the way that we process all the test points. If you want the posterior probabilities, which is, so remember with the perceptron algorithm, we just output this linear combination of inner products. With logistic regression, what we're going to do is, if we want the posterior probabilities, then apply the logistic function to that same expression. But if you don't want the posterior probabilities, if all you want is classification, is this point in class C or is it not, you can actually leave out the S, because all you need is the sign of this sum, in which case this becomes exactly the same as it is in the perceptron algorithm. But if you want posterior probabilities, then throw on that logistic function at the end. Any questions about that? All right, so I've shown you so far one kind of kernel, which is the polynomial kernel. I want to show you one more that's also used quite commonly in practice, popular, called the Gaussian kernel. Now, even though the polynomial kernel to me is already mind-blowing, I think this is even more mind-blowing because Now what we're going to do is we're going to say, okay, if I can use 100 million dimensional vectors in my lifted space, well, why not go all the way and just use an infinite dimensional vector? Well, yeah, you can do that too. So now we're going to essentially lift up our points, our sample points, into an infinite dimensional space. And that's going to give us something called the Gaussian kernel. Occasionally, you'll also see this referred to in the literature as the radial basis function kernel, which I think is not as good a name because there are a lot of different radial basis functions, but whatever. Oh. That's right. So, it starts with the following claim. There exists a lifted vector, phi of x, that has the following property, that if you compute the kernel function of x and z, in other words, if you compute the inner product of phi x and phi z, then it's equivalent to computing this. This is the result you get. It's essentially a Gaussian, which means it's a function that looks like the PDF of the normal distribution, although it's a normal distribution that's isotropic. The area under the function is not important, so it's not necessarily 1, but we don't need that. And you can think of it as being centered at z or centered at x, depending on your point of view. Now, when I say that there exists a phi of x that gives you that, in case you're curious, here's what it looks like in the very simple example of a one-dimensional feature space. So if each sample point is just a real number, then the following vector will do for you. I'm going to put a scalar at the start. All of the elements of this vector are multiplied by this same scalar, have the same scalar in them. So I'll just stick it at the beginning. And then here's the vector. The first element is 1 times that scalar. The second element is x over sigma times that scalar. But I'm also going to throw in a square root of 1 factorial. Well, that's just 1, but you'll see why that's there in a second. The next term is x squared over sigma squared times the square root of 2 factorial. The next term is x cubed over sigma cubed times square root of 3 factorial. Now, this goes on forever. So this is a vector having infinite length, infinite number of components. The components get smaller and smaller as you go down the line. And so therefore, if you take the inner product of 2 such vectors, say phi of x dot product with phi of z, then that gives you an infinite series. And the terms of that series get smaller and smaller, so they do converge to something. And the something that they converge to is, in fact, the kernel function xz that I drew up here. So that's something you could sit down and prove if you wanted to. Having said that, if you think that, it's kind of hard to imagine lifting up a point to an infinite dimensional space and then applying a linear classifier in that infinite dimensional space, I surely agree with you. At this point, when you're using kernels like this, the usual intuition of lifting a point into a high dimensional space, there's no intuition there anymore. It's gone. So this vector here is a curiosity. It doesn't really matter about it. People who work with Gaussian kernels instead think in terms of the kernel function itself rather than in terms of the lifted points. the key observation is that if you take this kernel and then do something on it like ridge regression, then the hypothesis is going to be in the following form. Just like it was before, it is a linear combination of kernel functions applied to your test point z. And that is a linear combination of Gaussian functions. And those Gaussian functions, there's one centered at each sample point. And the coefficients of that linear combination are the dual weights. So the Gaussians are a basis for this hypothesis. We're taking a linear combination of those basis Gaussians, and that gives us this. So this probably sounds very abstract like by now, so let me show you a picture, and suddenly it's going to be concrete. So here's an example. This is a regression that we get from 4 sample points. We used linear regression here. Now you might look at that and say, that doesn't look linear at all. That looks really curvy. Yeah, because it's a linear regression in an infinite dimensional space, and then when you map it back down, you get something curvy. Well, that part's a little hard to think of, but the part that's not hard to think of is, well, my sample points are, there's x1, there's x2. They're the peaks of those 2 bumps, or close to the peaks. There's x3, and there's x4. Those are close to the troughs of those 2 bumps. And the size of a bump, how high it goes or how low it goes, is dictated by the coefficient a. So, for instance, this bump, its coefficient is 1. This bump, you can see, is a little bit higher. Its coefficient is 1.4. This trough at x3, its coefficient is 1. And this trough x4, you can see it's not as deep as the other trough. Its coefficient is 0.7.